Good morning, everybody. Let's a little more participation up on that board there. Let's be monkeys, not sloths. Monkeys are agile and fast, and then sloths are kind of slow. And even though I love sloths, let's get some more participation up there on the board. Mrs. Larkin likes my analogy. All right, let's get that again. This is a concept we learned yesterday. So if you're kind of a little bit confused about it, it's at the top here. Electronegativity, ability to attract electrons, increases from right to left. Okay, from left to right, with the exception of those noble gases. Remember, noble gases, they don't want to be bothered with anybody. They're snobby, they're noble. They don't want to be with anybody because their valence electrons are already full. Okay. So just think about it. Box the atom that's probably the most electronegative, okay? Most electronegative in the highlighted box right here, in this red highlighted box, okay? In the red highlighted box. Good. I'm seeing some more answers up there. Good, excellent. Yeah, and I do agree with the answers that I'm seeing up there. Chlorine is the most electronegative when we're looking at this red box. If we're moving from left to right, again, being more, it wants to attract those electrons. It has 7 valence electrons. It needs 1 more. So it's going to be very highly electronegative because it wants to attract that 1 electron. Okay, so absolutely agree with you right there. Chlorine is excellent. So let's go ahead and move on here. What is something that you have made or created that you're proud of? And I love how it's not necessarily, and I've experienced this in my other classes, it's not necessarily a physical thing, but some people are emotionally, mentally, physically proud of something that they have done. Awesome. Remade a game in Roblox. See, that's awesome job there, Ignacio. I made a drawing for my friend Gabriel. That's sweet. That's pretty awesome. Some people are like, I'm really proud of myself for getting good grades last trimester. I mean, these are things that you should all be proud of. We're proud of you. I know me and Ms. Larkin are proud of you every day for the stuff that you teach us and that you are learning and that you're just amazing people. So just, be proud of yourselves for what you do because you are special. All right. So with that, I made coffee for my dad. Nice, Gabriel. Must have been nice. I tried to make coffee for my husband and I epically failed. I am not a coffee drinker, but I epically failed. And he was so nice. He's like, thanks, babe, but it's awful. But that's all right. So, all right, here we go. Let's go ahead and move on. Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box. Don't laugh, Mrs. Larkin, but it was an epic fail. It was like, ugh. And so please make sure that you don't put any personal information in the chat box for their protection and your protection. Participation is vital. Make sure you're respectful at all times and school appropriate. It was so bad. All right, attendance is already up in the chat box. Just scroll up. You should find our attendance word of the day. Remember, we do have the attendance for the first 15 minutes of class before we go ahead and clear out that room chat. Now, again, it does not mean that technically you do have until midnight tonight to get your attendance in. Make sure you copy the word down and that you spell it correctly to make sure that you can get full attendance credit. Okay, so you do have until midnight tonight technically, but only the first 15 minutes of class before we clear out that chat box. Okay. All right, so as I go through the schedule, make sure you get your attendance in. And obviously, once you get your attendance in, we're going to be asking you to open up your project. So go ahead and start that and start raising your hand once you get that project open and your attendance completed. So with that, our schedule today is we are in week 5 of 13 weeks together. I cannot believe it. 20 days out of our 60-day adventure. We're almost halfway through. We only have 10 more days and we're halfway through. Wow. It is Tuesday, January 5th, and we're going to talk about electronegativity within the groups, and we're going to do this through our 2J slides in our Chemistry Unit 2 element project. Okay. So with that, we are looking at what we have done and what we have to do, and we don't really have much to do. This is our last topic that we need to talk about in our elements. On tomorrow, or I believe it's tomorrow, you will have the Unit 2 project workday. So we'll have a workday where you can ask any questions. Come with your questions because no, sorry, Ignacio, class is not over yet. But come with your questions that we could help you out during this time period. So make sure that you are participating, and that if you need any help, this is the day to do it. We are on track for Thursday, January 7th is our turn-in day for this element project. Again, if you have any questions, please email us. We'll be happy to help you out with it on Thursday too. So nice try, Ignacio. But yeah, if you have any questions, let us know. So today what we're going to be doing is we're going to define groups on the periodic table. We're going to explain how electronegativity changes based on the atomic size and identify which atom in a group are more likely more electronegative. And we're going to do this all through slides 34 through 36. So if you have opened up your slides and are working on that, we are going to be starting on slide 34. So go ahead and move on down to slide 34. Make sure you get your hand raised because this is exactly where we're going to start.
Perfect. As mentioned, yes, raise your hands now if you have your project open and ready to go. Again, if you did it in Google Slides, you started it there. Here's the Google Slides folder, so you can open it up. Otherwise, if you did it in PowerPoint, open it up on your computer. If you have not started it, you absolutely have to get it started. All right, so I'm going to go ahead and send out, here's my grades tab, and then here is Mrs. Sepulveda's grades tab. Oh, sorry. Whose is that one? Oops, hold on one second. Here's Mrs. Sepulveda's grades tab right there. And so click on whichever one you are in. There's a Google Slide version where you can make a copy if you have a Google account, or a PowerPoint version that you can download if you have PowerPoint on your computer. One of those has to work, so you got to figure out how to make one of those work. Alternatively, you can take screenshots, photos, and then fill out the project once you are able to sit down and do it all at once. I'm fine with that as well. No worries, Mrs. Sepulveda. Again, I do want to mention that projects are the only assignment in our course, the only assignments in our course. So if you're not doing your project, you're not doing anything in our course. And so you won't pass our class because you're not earning a grade. So again, they're worth 85% of your grade. And so if you're like, I don't understand why my grade is so low, it's because we literally only have the projects. We only have completed the Unit 1 project, and then we will have the Unit 2 project due on Thursday. So those are the only two real assignments we have in our course. Yeah, yikes if you're not doing it. All right, I do need hands raised from everybody. If you do not raise your hand, we're going to be checking in with you. Again, if we have to check in with you multiple times and you're completely radio silent, we'll go ahead and log you out. So that's not cool. It probably tells us that you walked away from your computer or you muted us, which isn't great. So please make sure you respond. We'll give you a few chances. You either respond by raising your hand or responding to Mrs. Sepulveda's private chats. So we're still waiting on raised hands. Eric, Gabriel, Alexis, thank you, Eric. Keep your hands raised. There you go. Perfect. Waiting on Christopher, DJ, Tayan. Julia, send us a chat if you're good. And hold on, who else am I missing? Sorry. We're waiting on sorry, Gabriel, keep your hand raised. Don't put it down. Thank you, Tayan. Waiting on Gabriel, Christopher, DJ, Julia in the chat, Jalen, Anthony, Timothy, Ryan, and Catherine. Please raise your hand. Thank you, Gabriel. Leave it raised, Gabriel. You can't hear me? Can anyone else not hear me? Oh no, sorry. You're just kidding with me, aren't you? All right, let me see here. Gabriel, Christopher, DJ, Julia, Jalen, Ryan. You're the last 6 we haven't heard from. All right, we will be checking in with you. Again, you get a few chances to respond, and you do need to be responding to us. That's our bare minimum expectation, is that you at least raise your hand. Thank you, DJ. All right, perfect. Let's go ahead and move along. So I'm going to go ahead and send you in the chat box. Go ahead. Okay, you're here, Jalen? Okay, perfect. Sorry, 1 second. Let me just double check here. So we got DJ and we got Jalen. Perfect. All right, let me go ahead and lower those hands. Looking good. All right, everybody. So let's go ahead and talk about this. What is the same in each Bohr model of the Group 1 alkali metals? Go ahead and send that to me in the chat box. And what is different in each? What is different in each? Go ahead and tell me in the chat box what is the same or what is different. You can tell me either one, but go ahead and tell me in the chat. All right, I see Shelby. I see Gabriel. Again, yeah, so be specific. Which one's the same and which one's different? I do see some answers coming in, but let's be specific about which ones are the same in each one and which ones are different. All right, looking good. There we go. Perfect. Awesome. So I do see the similarities kind of coming in here. Lithium, sodium, and potassium, and rubidium, cesium, and fluorine, they all have the same number of valence electrons, which is how many? Tell me in the chat box. This should make sense because they're in Group 1. So they all have One, yes, one valence electron, perfect. And then the difference is what? There's a very obvious visual difference. Take a look at these. What's the difference between these? Compare lithium all the way to francium. What is the difference? I saw a lot of people already mentioning some options here. Tell me in the chat box. No worries, Anthony. Looking good. Yeah, so it has to do with their size, with their shells, absolutely. So we can see here that they are different sizes, and that is because they have different total electrons, right? So total electrons, which leads to more shells, which makes them larger, absolutely. So francium down here, for example, has 7 shells. It's way bigger than lithium. So this brings us back to connecting to learning about groups, something that we already learned about before, but we are going to go ahead and review today because it's related to today. So let's talk about this. Again, we mentioned yesterday a row is a period, and elements in the same row have the same shells. So taking a look here in row 1, period 1, they have 1 shell. Period 2, 2 shells. Period 3, 3 shells. Easy peasy, we learned that yesterday. Today, though, we're talking about columns, and columns have the same number of valence electrons. So taking a look here, for example, at group 17, they all have 7 valence electrons on their outermost shell, fluorine and chlorine. And we can see that as we go down in the periods, their shells are increasing, right, because that has to do with periods, but their valence electrons are staying the same. Smiley faces, emojis in the chat box if that makes sense. We're going to talk about that today, Shelby, so you're getting ahead of me because you are on top of it. So I promise we will get to that in just a moment. Perfect. All right, let's go ahead and apply that then. So yesterday we learned electronegativity is an atom's ability to attract electrons. And we learned the smaller you are, the more electronegative you actually are, because it's easier to reach new electrons, kind of how smaller atoms can grab new electrons more easily, like smaller hands, a child's hands can reach into small spaces more easily. Another way to think about it is like babies are cuter than adults, so the smaller you are cuter, or oftentimes some people might say that the shorter you are, the cuter you are, which I don't necessarily agree with. My husband is a foot taller than me, and I think he's pretty cute. But that is something that several students said helps them to remember. So I did want to mention that as well, if it helps you too. All right. So the smaller you are, the cuter you are. Okay. So based on this, which atom do you think is probably the most electronegative? Circle up on the board. If we know smaller atoms are more electronegative, let's apply that. Which of these is therefore the most electronegative? Circle it for me up on the board. Circle it for me up on the board. There we go. I see Kamari on the board. First one up there. Let's see who else we can get up there. I see Annabelle, Camilla, Malin, working hard. Let's get at least 10 people up there. We got 30 of you. That should be easy peasy. Thank you, Daniel. Thank you, Gabriel. I see Shelby. Perfect. All right, let me go ahead, pause those tools, and let's talk about it. Oh no, Ignacio, I doubt that. Everybody's got some redeeming factors. So taking a look here, lithium is definitely the smallest, definitely the cutest, and therefore the most attractive to electrons. So let me go ahead and write that up here if I can find some space, because there's not a lot of space here. Here we go, come on. All right, so here we go. So lithium is the smallest because it has the least shells. Least shells, and therefore it's the most electronegative. Most electronegative. Perfect. All right, now let's go ahead and do the opposite on the whiteboard for me. Please box the one that is probably the least electronegative. Let's think about the opposite. If small atoms are more electronegative, then what would be the opposite? Which one is the least electronegative? Go ahead and circle it for me up on the board. Circle or box. You don't have to circle. It can be a box. Just indicate it for me in some way. We're going to go ahead and send out the attendance one more time, and then the chat box will be erased when my next timer goes off. So please make sure you open up your attendance and enter the start of class word if you haven't already. Do it now or forever hold your peace. Looking good. Looks like we agree here. Absolutely. Francium is for sure going to be the least electronegative because it's the biggest, right? It's big and cumbersome. It's got a lot going on already. It's like, dude, I cannot handle more electrons. I already have so many. It's kind of like people who have a lot of kids are like, I don't know if I can have another kid. I think we might be good here. So this one's the biggest. It has the most shells, and therefore it is actually the least electronegative of these 6 atoms here. Smiley faces, emojis if you feel comfortable with that. Smiley faces, emojis if you feel comfortable with that. Beautiful. All right, so let's go ahead and now let's bring this all together and connect these two things. So as we move top to bottom within the same group, also sometimes called a column or a family, and we're going to go ahead and clear the chat now. Okay. Electronegativity, is it increasing, decreasing, or staying the same? So again, lithium is the most electronegative, or is more electronegative. And down here, rubidium is less electronegative. I couldn't fit cesium and francium, so I just ended at rubidium. So based on this, if we're going from more electronegative to less electronegativity as we go down, is that increasing in electronegativity or decreasing? Tell me in the chat. If we start off higher here, lower down here, is that increasing or decreasing as we go to the bottom? Excellent. Yes, perfect. I see lots of people answering. I would agree. Electronegativity absolutely decreases. Absolutely decreases here. We can see that right again. We start off high, we get smaller, that's a decrease. Now again, this has to do with both size as well as a new concept that we haven't yet learned. So again, as we get more shells, that means we're getting larger, and so it's harder to attract electrons, right? Rubidium, again, has a lot going on. It's already attracting a lot of electrons. It's going to be hard for it to attract another electron because it's already got so many, okay? Additionally, there's another compounding factor called shielding. So these innermost shells are also blocking the nucleus from the outermost shell. So the inner shells are interfering with protons. Remember, protons are positive and opposites attract, so they're the ones that are attracting those negative electrons. So it's really hard for these protons to move through all of these shells to try to attract another electron out here. It's just, there's a lot going on, they're being shielded, and so rubidium's just really bad at attracting electrons. Go ahead, give me a smiley emoji if you feel comfortable with that. Smiley emoji if you feel comfortable with that, if you understand. Again, the bigger you are, the less attractive you are. In terms of electrons. I don't mean in real life. Although, again, I do hold that babies are cuter than adults. Cool beans. All right, let's make sure we fill in slide number 34.
All right, so let's look at slide number 34. Everybody should be on that slide. And if you look at the top there, you're going to see that yellow box that says type here. You're going to write the word decrease. And I'm going to go ahead and just type it in here. Let me change my color. I don't like that black color. Here we go. Decrease. If I could. Okay, there you go. So go ahead and just type that word decrease into there because again, just like Mrs. Larkin said, from the top to the bottom in the same column or same family, it's going to decrease. Perfect. Thank you, Mrs. Larkin. All right, we're going to give you about, let's see, 20 seconds to put that number in. Once you get that those letters in or that word in, we're going to go ahead and just check in with you. So raise your hand when you are finished. Raise your hand when you are finished. Go, go, go. 20 seconds up on the clock. I see a lot of people working hard. There goes my alarm. And there goes my other one. All right, there we go. Let's check in with a couple of people. Angelo, Gabriel, Alexis, Taylor, Destin, Tayan, Jalen, Kamari, Tim, Ryan, Catherine, Adriana, Dion, Julia. Again, I have private chat at a couple of you. Make sure you're participating if we don't hear from you. If we don't hear from you, then we assume that you walked away or you muted us, and that is not a good go. Last call, Angelo, Gabriel, Alexis, Destin, Jaylin, Tim, Ryan, Catherine, Dion, and Julia. Make sure you are, and again, if you're working on a cell phone, just let us know in the chat box. Just give us an emoji that I'm checking in with. I said just letting us know that you're with us, that you're participating, you're working. Type on slide number 34. This should not take a lot of time. Angelo, Gabriel, Alexis, Dustin, Jaylin, Ryan, Catherine, Dion, and Julia. I will be checking in with a lot of people. All right.
All right, perfect. So let's go ahead and begin to actually apply this. So I'm going to give you your whiteboard tools, and up on the board, which of these elements is likely the most electronegative? Again, the ones with less shells are smaller and more electronegative. All right, so taking a look here, remember that shells are related to periods. So period 1 has 1, period 2 has 2, 3 has 3, 4, 5, and 6. So based on this circle up on the board, which one has the least amount of shells in this group? In group 14, our carbon family, and therefore is the smallest, and therefore is the most electronegative. Get your answers up there. I see Malin up there. I see Shelby up there. I see Camilla working. All right, get your answers up there. Perfect. Thank you, Daniel. Yeah, no worries, Anthony. Yes, perfect. Let me go ahead and pause those tools. I would absolutely agree with everyone. Carbon is going to be the smallest here. Carbon only has 2 shells because it's in period 2, whereas all of these have more shells, therefore carbon's the smallest, therefore it's the most electronegative. It can reach out and grab a new electron the easiest. Remember, whereas lead down here has a lot going on. It's taking care of 6 different shells. There's some shielding going on, blocking the protons from attracting new electrons. So lead down here, definitely not very electronegative. Great job, everybody. Let's go ahead and give me a smiley or emoji in the chat box if you feel like you can do the next one on your own. Again, you're looking for the group in the group, the atom with the least shells at the top. It's smaller, it's more electronegative because it's cute. It is cute. All right, looking good. Let's go ahead and do this next one on our own. Here we go.
A couple of hints up there for you. Remember which element has a higher electronegativity. Remember, we're looking at the red box right here, the red box. Remember, less shells equals smaller, cuter, and more electronegative. So just kind of give you, all you need to do is make an X right over here on this left-hand side. X in the left-hand side. Once you've done that, go ahead and give us a hand raise. If you want to check in with us, we're more than happy to check in with you. Go ahead and put it into the question answers box. Please do not put any answers in the room chat. Please do not put any answers in the room chat. Go ahead and just put go into the question and answers box. We're going to give you only about 20 seconds to do this. Go, go, go. Alrighty, so we have 20 seconds up on the clock. Again, I'll give you a couple more seconds to kind of fill in your answers here while we just check in with a few people. While we check in with a few people. Alrighty, so just again, if I call your name more than 3 times, which some of you we have, then you will be dismissed. Angelo, Gabriel, Destin, Jalen, Tim, Ryan, Dion, and Julia. Please make sure that you are raising your hand. But again, we do want to reiterate, please do not put any answers into the chat, to the main room chat. Angelo, Gabriel, Destin, Tim, Ryan, Dion, and Julia. Last call. All right, thank you so much.
All right, so let's go ahead and begin to synthesize this all together. So we learned a lot about electronegativity in periods yesterday and an electronegativity in groups today, okay? So again, smaller atoms are more electronegative. They're more attractive to electrons. Again, think about they're smaller, they're cuter, like babies are cuter. All right, so in periods or rows, we learned yesterday, atoms have the same number of shells. So let's take a look here at this example in row 2, period 2. They all have 2 valence shells. That's why they're in period 2. So electronegativity is going to get higher to the right because they are working with the same number of shells. So taking a look here, carbon versus nitrogen, nitrogen's more to the right. Nitrogen has more protons to pull in that same shell. Smiley faces, emojis if that makes sense. Smiley faces, emojis if that makes sense. They're pulling in the same exact shell, so it ends up being smaller. It ends up actually being smaller. Okay, no worries. Thank you, Ryan. All right, and so the exception here is, again, we ignore noble gases because, again, noble gases already have full valences. Sorry, I'm going to help a student really quickly. Give me one moment here. Let me share this really quickly. Kamari, can you see my screen? Okay, so here we go. I'm going to go ahead and show this to you. So if you go to your grades tab, which is right here, so grades tab right here, let me show it to you as a student. Okay, so if you go to your grades tab right here, okay, you will see, scroll down, here's the Unit 2 project. So there's a Google Slides version if you have a Google Slide, if you have a Google account, or a PowerPoint version. So you probably have PowerPoint on your computer. I'll show that to you. So here's the PowerPoint version. Okay, so you're gonna download it to wherever it downloads to. Okay, and then when you open it up, you'll see the project that everybody's working on. So it'll pop up in just a moment. I apologize, everyone, but I want to make sure everyone has access to the projects, right? So we're currently on slide number 34, 35. We just did slide 35 right here. Does that make sense? Perfect. Okay, awesome, everybody. Apologies for that. Let me jump back over here. Thank you for being patient. All right, let me go ahead and jump back into our PowerPoint. And here we go. Okay. Beautiful. Okay, so let's go ahead and take a look here. So groups, though, on the other hand, we talked about groups actually have different numbers of shells, right? In periods, they all have the same shell. They're all working with the same structure. But groups actually have different shells. So taking a look here, fluorine, chlorine, bromine, iodine, acetine are all in this group 7 over here, 17. And as you go down, they have more shells, right? So this one only has 2, this one has 3, 4, 5, 6, and so on and so forth. So the smallest one is actually the one with the least shells at the top. So taking a look here, fluorine is both the smallest in its row because it has the most protons to pull in its shell of that row, and it also has the least amount of shells in its group, so it's also the smallest in its group. That is why fluorine is in fact the most electronegative element on the entire periodic table. Smiley faces, emojis if you understand that pattern. The more you go to the right, the smaller you are. The more you go to the top, the smaller you are. And therefore, the more attractive. Smaller is cute in this case. Okay, let's go ahead and apply that. So you have your whiteboard tools. Which of these elements, therefore, is the most electronegative? So again, we want to go more to the right and more to the top, right? Because that makes us smaller. So taking a look at these 9, which one is most to the right and most to the top? Circle or box it for me up on the board. Go, go, go. Perfect. I see Annabelle up on the board. I see Shelby. Get your participation up there. Let's get at least 10 people working hard up there. There we go. I see Anthony in the chat box. Perfect. There we go. I see Derek up on the board. Camilla working hard. Yes, perfect. Let me go ahead and pause this before it gets too complex up here. But yes, sulfur is the element that's furthest to the right and furthest to the top. Let's go ahead and I'll actually make this super clear here. So again, if we are looking at rows, we want the ones that are furthest to the right in rows. So that would be sulfur here, that would be selenium and tellurium. They are the furthest to the right in each of their rows, and therefore the smallest, right? They have more protons to pull in the same valence as the other atoms in their row, in their period. Okay, so that makes them smaller. Now, on the other hand, if we're looking at each group, then we want to look at all of the atoms at the top. Because remember, the atoms at the top have less shells, right? 1, 2, 3, 4, 5, 6. So right here, silicon, phosphorus, and sulfur all only have 3 valence shells. Therefore, they're the smallest in each of their groups. And so where that overlaps, that's the one that's both furthest to the right and furthest to the top, and therefore our correct answer here is absolutely sulfur. Smiley faces, emojis if that analysis makes sense to you. I know not everybody got a chance to participate on the board before I stopped the tools, so I want to make sure everybody feels good with that. Thank you, Annabelle. Thank you, Camilla. Thank you, Miles, Shelby. I see y'all in the chat. Let's make sure we're working hard in the chat, everybody. Christopher, let me know if you had a question. I saw your hand raised. Thank you, Anthony. Looking good. All right, everyone. So let's go ahead and work on a matching activity. Now this is actually bringing together some stuff that we learned from a previous unit, which is that metals are electron poor. So remember, metals are electron poor, and the poor get poorer, right? So remember that metals actually lose electrons. So if they're losing electrons, you want to be thinking to yourself, does that make them highly electronegative and attractive? Or does that make them low electronegative and less attractive if they're losing electrons, okay? Another way to think about it is the electron-poor metals are all found on the left of the period. The left of the period. Now, electron-rich nonmetals, on the other hand, are rich, and the rich get richer. So the rich get richer, they actually gain electrons. That's something we learned about in a previous unit. And another way to think about it is they are on the right side of a period. They are on the right side of a period. Then lastly, right down here, large elements that have more electron shells, are they more electronegative or less? Again, remember that large elements have a lot going on. So think about, are they going to be able to be attractive to electrons or not? And then small elements, remember, are cute. They're small and cute. Think about, is it easier for them to reach electrons, yes or no? Go ahead, grab your whiteboard tools. Please use your line tools if you can. Just click on the square and then change it to a line and match those up. Otherwise, feel free to use the pen tool. The pen tool's right here. Go ahead, get your answers up there. Cool, I see Annabelle working. I see Gabriel working. Get your answers up there, everybody. Cool, I see Camilla up on the board. I see Daniel up on the board. Perfect. I see Shelby working hard. I see Ignacio doing something. Oh, there you go. Perfect, Ignacio. There we go. I was like, I don't think that line goes anywhere, Ignacio. I see Anthony. Beautiful. All right, let me go ahead and pause these tools. We're looking good up here. So I'll go ahead and clear this out in just a moment because I do want to make sure we make sense of all of this. But it does look like we said higher electronegativity is the electron rich and the ones that are small. And lower electronegativity is the electron poor and the ones that are large. Let's go ahead and make sure that that makes sense. So taking a look here, you are more electronegative the smaller you are. So first off, we should absolutely be able to guess that small elements with less electron shells are more electronegative. And that should make sense because they're at the top of their groups, just like fluorine is at the top of its group. We also mentioned that fluorine's on the right side of a period, and so fluorine is absolutely going to be more electronegative again in its row. And again, the rich get richer. They actually gain electrons, meaning they're highly attractive to electrons. Think about a lot of times in society, rich people are considered more attractive to some people, right? So the richer you are, sometimes you're considered more attractive because you got lots of moolah, and the same thing is true with electrons. If you already have most of your electrons, it's a lot easier for you to gain more electrons. Smiley faces, emojis in the chat box if that makes sense. The rich get richer. They are better at gaining electrons. Thank you, Annabelle. Thank you, Anthony's, Miss Fulvina, Camilla. Now, on the other hand, lower electronegativity means you don't have a lot of electrons and you'd rather give them away. If you give away electrons, that means you're not attractive to electrons. That means you're literally getting rid of them. You're literally unattractive to electrons. They're also on the left side of the period, which means they don't have many protons to pull in their valence shell, so they're a lot larger. So we mentioned here, right, they have fewer protons, and so they're larger. Whereas over here, as you go further to the right, again, you're going to have more more protons to pull in the shell, and so you're smaller. Okay, so again, smaller is cuter, smaller is better at attracting. All right, and again, same thing here. Larger is going to be less electronegative because they're too big. They're too cumbersome. They have a lot going on. They also have shielding from all of those shells, preventing that nucleus, preventing those protons from attracting any more shells. Let's make sure that we get this into our project. Here we go.
And drag, so you can click and drag it, or you can actually use arrows. It doesn't matter, but we do have it set up for a click and drag. So go ahead and match these up to the correct one. Again, electron-rich nonmetals are going to be higher electronegative, and smaller elements with less electron shells, higher electronegative. And then, as you could say, the poor metals are going to be lower electronegative, and the large elements are going to be less electronegative, so lower electronegativity. So go ahead and click and drag, just or use your arrows. It does not matter to us. Just make sure that you get this in. We're going to give you 25 seconds to do that. Please raise your hand once you got that in. Go, go, go. Cell phone or with your computer, or quickly write this down because we do need to get moving because of our time. So just make sure that you are aware of that because the timer's up now. All right, let's go ahead and check in with a few people. Just reading a couple of chats. Here we go. Oh my goodness gracious. Good job, everybody. Patrick, Gabriel, Alexis, Taylor, Kamari, Tim, Catherine, Julia, and Ryan. Let's get our hands raised up there. Thank you so much. Those who are getting their hand raised. Thank you, Kamari. Thank you, Taylor, I think. Patrick, beautiful. Thank you so much. Gabriel, Alexis, Tim, Catherine, Julia, Ryan. Ryan, Julia, Catherine, Tim, Alexis, and Gabriel. Let's get our hands up. Oh, are you making fun of my ringer? Don't worry, folks. I mean, I can always change it up for y'all. Alexis, Tim, Catherine, Julia, and Ryan. Let's get our hands up. All right. Again, if you missed it, gonna have to watch the recording later on this afternoon.
Perfect. Okay, so I do want to talk a little bit about the project slides that we're going to be talking about tomorrow. So don't freak out now, but I do want to go ahead and go over it while we have this fresh in our brains. So what is your element's size compared to other elements in its period or row? So remember that the further to the right you get, the smaller you get. And again, that's because you have more protons to pull in the same valence shell, because everybody in the same period has the same valence shell, right? So if you're taking a look at your element on the periodic table and you're like, wow, it's pretty far to the right, it's probably very small. So you would say small. And why? Because it has more protons to pull in the same valence shell. If yours is all the way to the left, you say it's large. And the reason is because it has less protons to pull in the same valence shell. Okay, smiley faces, emojis, if that makes sense. Okay, so I have both, like the explanation here and the reasoning. So don't forget the reasoning, because you have to explain why. Okay, and again, I will include this in the recording for tomorrow, and if it's still confusing, you can ask for help during live session as well, okay, during our work time. Then, what is your element's size compared to other elements in its group or column? So again, this one has to do with the number of shells overall, right? So, oops, come on, here we go. All right, so taking a look here, element size compared to other elements in its group, again, they are smaller at the top. So at the top, you are smaller, and that is because you have less shells, right? Period. If you're at the top in period 2 or 1, you only have 2 or 1 shells. In the middle, periods 4, 5, 3, right? You're going to be medium size, and if you're at the bottom, you have the most shells. So you have 5 or 6 shells, right? Okay. Yeah, screenshots work well here. So you can explain I'm small, I'm large, I'm medium based on my number of shells. Okay. Now, based on that, then put that together and figure out, does your element probably have a high or low electronegativity? So if you're small and small, you probably have a very high electronegativity, because the smaller you are, the higher electronegativity you have. So smaller equals higher electronegativity. If you're large and large, then you probably have a lower electronegativity. If you're medium and large, again, probably still lower. If you're small and medium, probably a little bit higher. Now, there is a cool thing that on ptable.com, and I will show this to you tomorrow, ptable.com. You can actually look at the numerical data for the electronegativity. So you can both think about conceptually probably what is going on with electronegativity, and then look up the actual answer on ptable.com. And again, I will show that to you tomorrow as well. So don't freak out. Again, all of that information is absolutely available to you. And then based on its electronegativity, is it better at gaining or losing electrons? Remember, if you have a high electronegativity, then you are better at gaining electrons, right? That's our nonmetals. They have most of their electrons. They are small in their rows, and so they want more electrons. Whereas if you have a lower electronegativity, you're actually going to be losing electrons. You're really bad at gaining them. You're not very attractive, and so you lose electrons. Make sure you take a picture of this if this helps up now. Make sure you take a picture of this if you need it now. Perfect. All right, looking good. Awesome. So there we go. Now reflection, slide 38. This one's easy peasy. You just need to tell me the most interesting thing you learned or reviewed about your element. Again, a lot of our elements, as you're researching, you're probably learning some pretty cool stuff about them. So tell me, what's the most interesting thing that you learned? And then something that went well, something you can do to improve next time. For these two, a reminder, please do not put I don't know, and please do not put nothing or everything, because those are not real answers. I want specific points. So specifically something that went well, specifically something you can do to improve. We can all get better, so there's always something you can do. Excellent. All right, we talked about groups and electronegativity. And I think we're out of time, so I'll go ahead and just wrap us up here. Let me stop our recordings.